Hello, I'm Michael Battaglia. I'm a postdoctoral associate at Yale in the Department of Earth and Planetary Sciences, and I'm excited to share with you some results comparing the Mars dust activity database to two reanalysis data sets. First of all, the MDAD shows dust activity throughout 8 Mars years. Here's a frequency map showing where dust storms are most prolific. They form in Acidalia, Utopia, and Arcadia in the Northern Hemisphere, and to some extent near Argyre in the Southern Hemisphere, but we'll focus on the Northern Hemisphere here. In the Mars dust activity database, there are about 15,000 dust storm instances, which are single enclosed areas of dust activity on a given sol. We can connect the movement of these individual instances together to form a dust storm member, and collections of these members following a similar trajectory over 3 or more sols are deemed sequences, following the terminology set up by Helen Wang. Within these sequences, the motion of these sequences mostly is circumpolar around the north and south poles, but many of them travel from the high latitudes to the lower latitudes in a behavior we call flushing. When these storms flush, that's when we get the major, larger sequences of regional dust storm activity. The example I'm going to focus in for this talk is the quote unquote A storm by the terminology by Cassadal 2016 from Mars year 31. And it's really a 2-component dust storm. The main component is a flushing dust storm from Utopia down into Hellas, but there is a little bit of flushing activity from Acidalia as well. To put this in context, we're only going to focus in on a very small period of time when the Northern Hemisphere baroclinic eddies were most important for the development of this A storm. And this A storm contributes most of the opacity shown here in green for Mars year 31 before the winter solstice. Again, the gold storm is the entirety of the A event, but we're only going to focus in on a small portion of that. So from here on out, we're going to look at Mars daily global maps taken from the data set that Helen Wang and I have on PDS. This is version 2.0. And on top of that, in gold, are outlined the storms from the MDAD. In addition to that, I've taken the eddy analysis from 2 reanalysis data sets, Open Mars at the top and a single eMars member at the bottom. We're looking at the member instead of the mean, because the mean has a tendency to smear eddies together, especially during the MCS time when data are assimilated into the models, because the lowest levels are not constrained really well by MCS temperature retrievals. And so the mean kind of smears eddies out. And so to compare to the single deterministic diagnosis of Open Mars, we're only going to look at the member from eMars. So from these data sets, these are the time deviations from the time mean eddies of the winds, which are the arrows. The white contours show the eddy surface pressure, solid or positive, dashed or negative, and the eddy surface temperatures. Red and solid are warm, dashed, dot dashed, and blue are cold. In addition, I will point out where the high and low pressure systems are. So immediately you'll note that the eddy low pressure systems are eddy warm areas. This makes sense if these are baroclinic cyclones, because cyclonic anti-clockwise motion around these centers of low pressure bring warm air from the equator northwards and cold air southwards. So these are eddy warm regions. We're now going to compare the motion of these particular 2 eddies over the course of 7 sols. And we're going to compare this to a widely used cyclone model for Earth called the Norwegian cyclone model that's been around for about 100 years. So we're looking at sort of stage 1 or stage 0, right now, where there's simply flow along the polar front, where we have cold temperatures in the high latitudes. This is winter under the polar hood, and where it's clear and the sunlight is reaching the ground, it's still warm near the equator. So we have this large meridional temperature gradient set up. And so baroclinic instability is favored, and that's what spins up these cyclones and anticyclones. So here's stage 0. We're starting to see cyclones begin to form, undulations in the polar front begin to form. This is we're moving on to day 3 now. So we're looking at stage 1. This is the incipient frontal cyclones. This is when cyclones finally begin to form. We see the deepening of the high and low pressure centers, more so in EMARS than in open Mars. And we'll see throughout the rest of these next few sols that there are a lot of differences between the 2 reanalysis data sets, although they do compare quite well. There are some differences between them. And we can start to begin to draw fronts onto this map. I'm only doing it for EMARS down at the bottom in this particular slide. And there are warm fronts to the east or the right and cold fronts to the west. And these 2 regions will begin to catch up to one another as we move on to stage 2, where we begin to see deepening of the cyclone. The cold front is beginning to sweep down and equatorward, and we start to see this nice frontal morphology showing up around the cyclones, especially here in EMARS. It matches up really well with the dust storm morphology. And again, we're seeing that there are high pressure centers behind the cold fronts. And this is where we see a lot of the dust lofted up after the fact. And we'll see this more prolifically as we move on into stage 3, where we begin to get to the mature stage of these cyclones. The eddies are kind of reaching their strongest extent, the coldest and warmest temperatures and the deepest, highest and lows. The cold front is really beginning to catch up to the warm front. We're starting to get occlusion right near the low pressure centers. The dust storms are really following quite closely where the winds are shifting and changing. This is showing where the eddies are the strongest in both data sets. And again, we get strong high pressure and cold air moving down behind the dust storms. Follow this now into stage 4, where we're beginning to see the decay of these cyclones, and we're starting to see these fronts begin to move down away from the polar front and towards the equator. Again, high pressure is moving in behind them, and this high pressure is cold, partly due to the opacity in the mid-levels from the dust. As I showed in my 2016 paper, we're beginning to shut off the baroclinic instability that's forming these cyclones. And the dust is beginning to leave the baroclinic region, where it will finally begin to reach the southern hemisphere and then grow into much larger cyclones. At this point, we're starting to see the decay of these cyclones. But we'll also note there are large discrepancies still between the 2 data sets. For example, there are much colder temperatures here in the EMARS member, and we have opposing directions of wind in the Acidalia region. Again, this is because the Mars Climate Sounder database does a poor job of constraining the data to a single solution, as can be seen here in this Havmøller, where we have much more coherent waves for open Mars at this particular time, at least, than we do for EMARS. Again, if you'd like to know more about this, please see my paper in JAZ. As a final conclusion, I'll just note, even though there are some discrepancies, we can turn to an energetics analysis, which I go to in depth in a paper I hope is coming out soon in the Journal of Atmospheric Sciences. Here, I'm just showing the baroclinic conversion positive in the red contours and barotropic energy conversion negative in the blue contours and eddy kinetic energy in the shading. And this is just a map showing all of the individual sols that we just looked at. And there's good agreement between all of the data sets for this time, which should give us confidence that they are showing a coherent path and development of these eddies in time. So this leads me to conclude that we're emerging into a brand new and exciting subdiscipline for Mars meteorology, that of surface frontal analysis, where we can use techniques that have been applied for extratropical analysis for Earth, looking at, for example, nor'easters, or atmospheric rivers and apply the Norwegian cyclone model to Mars. There are good comparisons between both reanalysis data sets, but there are some problems constraining these due to issues in the MCS era. Again, I invite you all to please go look at the Mars Dust Activity Database. It's freely available on the Harvard Dataverse, and please contact me if you have additional questions, and I look forward to the live Q&A. Thanks.